In this paper, we study a new objective for Markov decision processes called transience, which asks that no state is visited infinitely often. This, of course, is only possible for infinite state MDPs. We are interested specifically in the internal complexity of strategies and show that transience admits very simple, namely memoryless and deterministic epsilon optimal strategies. This works even in the presence of infinite branching. We can find uniform such strategies, meaning epsilon optimal from every starting state. We also show that if optimal, i.e. zero optimal strategies exist, which is not always the case, then again also MD ones exist as well. Finally, we consider MDPs where all strategies ensure transience almost surely. Such universally transient MDPs strictly generalize acyclic ones. And it turns out they allow for simpler strategies for some classical omega regular objectives.
Hello, I'm Eric Munday. In this teaser talk on the strategy complexity of mean payoff, total payoff, and point payoff objectives in countable MDPs, I will give you a taste of the results we have obtained. The objectives we consider are the limit of the aforementioned mean, total, and point payoffs. That is to say, we would like to eventually, forever, push for payoffs above zero or have them converging to zero. In this way, limit objectives are a sort of quantitative generalization of co-duty objectives. We have considered strategies that are memoryless, as well as those employing a step counter and/or a reward counter as memory. A step counter is a clock tracking the number of transitions taken so far. A reward counter tracks the total reward collected so far. Both are forms of infinite memory, albeit very limited forms. You see before you a table of our results. All entries in the table are tight in the sense that they are both upper and lower bounds. Lower bounds are obtained from counterexamples, and upper bounds are obtained from a proof. All strategies are deterministic, and randomization does not help here. Thank you for listening to this teaser talk. If you are interested in hearing about the results in greater detail, please watch the main talk. Thank you.
Hello everyone, our work is about model checking quantum continuous time Markov chains. There are a lot of works on model checking classical Markov chains for both discrete time and continuous time. As quantum computation develops fast, there is an urgent need to develop effective verification techniques to improve the trustworthiness of quantum systems. So the counterpart model of quantum system has been considered in this years. For instance, the quantum discrete time Markov chain. While continuous time system is more realistic in physical world, we initialize model checking of the quantum continuous time Markov chain, QCTMC. Here is the structure of our main idea. As a real-time system, we specify the temporal properties on QCTMC by signal-temporal logic, STL. To effectively check the atomic propositions in STL, we develop a state-of-the-art real-root isolation algorithm under Shanel's conjecture. Further, we check the general STL formula by interval operations with a bottom-up fashion. Finally, we provide a running example of an open quantum work to demonstrate our method. Our contributions are threefold as follows. We are looking forward to your questions and comments.